Hi dear students, the last class we derived the formulas of moment of inertia of some simple objects like a disk, ring, solid sphere, hollow sphere, solid cylinder and also the hollow cylinder. We also explained the tricks to remember the formula of those objects, and today we proceed the discussion with the parallel axis theorem. Let me consider first the rotation of an object about a particular axis. This is a rectangular lamina and it is rotating about this axis. Let me call this is a case A, and moment of inertia of this object that we can simply calculate using this expression m r square. Maybe you can mention that this is the distance r to this particular point. And another case B, the same lamina that rotate about an axis that passes through the center. Now the distance from the axis to that particular point is, let me call this is r. Let me, this is 2 centimeter roughly, and this is 5 centimeter. And the moment of inertia of this lamina can be find out using this equation I is equal to mr square. You know that the moment of inertia is different in the both cases because the r, the mass distribution, is at a larger distance in the case A because r is larger. Therefore, the moment of inertia is larger in the case A. And in the case of B, the mass distribution from the axis is little bit closer, means r is smaller compared to the case A. Therefore, if the r is smaller, then the moment of inertia is smaller. Then how we will calculate accurately the moment of inertia in these two cases? For that we will use the parallel axis theorem. That is, in general, if you have a body like this and we have calculated the moment of inertia of different objects about the natural axis, that is, natural axis is this one, that is, this is the axis passing through the center of mass point and perpendicular to the plane of the body. And the moment of inertia of a disk that we have derived, moment of inertia is, this is a disk, therefore divide by the smallest number, therefore mr square by 2. And this axis is the natural axis. Natural axis means an axis passing through the center of mass point and perpendicular to the plane. Fine. Now, if the body is rotating about this particular axis, I call this is a z prime and z. This is a point O. It is given that this axis is at a distance A from the natural axis. Then the moment of inertia about this z axis, that can be denoted by Iz, and the moment of inertia about the center of mass axis, that is nothing but the natural axis I explained in the last class, is Icm. Then the parallel axis theorem says that moment of inertia about the z dash axis, that is Iz is equal to I center of mass plus mass into distance between the two axes square, a square, where m is the total mass of this body. Then how we can state this parallel axis theorem? The theorem states that the moment of inertia of a body about an axis that is here the z-axis, that is equal to the sum of the moment of inertia of the body about a parallel axis passing through the center of mass of the body, and product of the mass and square of the distance between the two parallel axes, that is this a square. That is the statement of the parallel axis theorem. Moment of inertia of a body about any axis is equal to the sum of the moment of inertia of the body about a parallel axis passing through the center of mass of the body, and product of the mass of the body and square of the distance between the two parallel axes. This is the statement of the parallel axis theorem. Fine. Now let us apply this parallel axis theorem to find out the moment of inertia of the different object when it rotates about a particular axis. The first one is this is the first question, that find moment of inertia of a thin rod rotating about an axis normal to it and passing through one end or passing through the corner. That is this is the rod or the stick, and this is the axis which is passing through the one corner, or we can say this is axis passing through the end of the stick. Let us call this is the axis z, z dash axis, and we need to find out the moment of inertia about iz. Fine. Now, or we know the equation for the moment of inertia of the stick about the center of mass axis, or we can say moment of inertia about the natural axis, and the distance from this center of mass to the given axis, that is a. Then we can write the parallel axis theorem. Iz, that is equal to I center of mass plus m a square. Actually this a is the distance between the two axes. Fine. Now we know that if a rod is rotating about an axis, that axis passes through the center of mass point and perpendicular to the length of the stick. Then this axis exactly cut the rod like this. Then one can write this is a 1 and 2, and the I center of mass, now that is this axis, you know that expression m l square by 2. It is given that in the question, this should be noted here, this is the total length of the stick that is given. Okay. Now this is m l square, this is not 2, this is 112. Moment of inertia about the natural axis. Moment of inertia about the axis passing through the middle of the stick. M l square by 12 plus m. Next we have to write this a. This a in terms of the L. If you look at this picture, then it is very clear that this distance, that is nothing but the L by 2, that is a is equal to L by 2. Fine. This is instead of a you can substitute L by 2 whole square. This will be m l square by 12 plus m l square by 4. This will be m l square by 3. Actually we have derived this expression in the previous class, that is moment of inertia of the stick about an axis passing through the corner, that was we derived yesterday ml square by 3. Okay, there is one question that you can do as a homework, because this kind of problems we might have practiced in your +1 class. The second question is find moment of inertia of the disk about an axis passing through the circumference and normal to the plane. Okay, this is the disk rotates about this axis. We need to calculate the moment of inertia. Let me write this is a this axis is given as a in the question. That is, let us calculate IA is need to be calculated. This IA is equal to we know that the general expression for the parallel axis theorem, that is, we can write I center of mass plus mass into distance between the two axes. Okay, it's a square. The center of mass axis is this is one that everybody knows. This is the center of mass axis, natural axis. Moment of inertia about the center of mass, that is mr square by 2, because this is a disk, plus m. A is the distance between the two axes. There is nothing but r square, because A is equal to r. And the answer is 3mr square by 2. Fine. Lot of problems you can see in the question papers, and please practice this. Now let us move to the next topic, that is dynamics of pure rotation about an axis. Here we discuss dynamics of pure rotation about an axis. Actually, the main discussion here is the dynamics of a rigid body rotating about a fixed axis. Fine. Actually, the rotation is pure rotation. Pure rotation means here no translation, no translational motion. Suppose if I consider a ring or a disc, then this ring rotate about this axis. There is no translation, pure rotation, only rotation. The examples of this pure rotation, I can suggest the rotation of a flywheel. You have done experiment with the flywheel in the laboratory. Rotation of flywheel, and motion of door. Specifically, if we say motion of a door in its hinges. Another example is motion of a fan blade. You might have noticed the blade of a fan that is purely undergoes a rotation. There is no translation in all these cases. Fine. Here we are talking about the pure rotation case without any translation. Fine. For this, consider a body rotating about an axis. This body rotates about an angular speed omega. Let us say this omega is the angular velocity. This motion is about a z-axis. Therefore, the angular momentum of this rotating object, that is I omega, we have already derived. This is nothing but the z component of the angular momentum, or we can say this is nothing but angular momentum, where I is the moment of inertia of the body. Fine. Now, the external torque acting on the system. You know that if this object wants to rotate in this direction, some external torque must be acting on it. The external torque acting on the system. Let us write that is tau. Tau is equal to, you know that the expression for the torque we already derived in the last unit, that is dl by dt. Rate of change of angular momentum is a torque. Now here you can replace this L by this I omega. Therefore, d by dt of I omega. Moment of inertia of the disk is constant. We can take it outside. D by dt omega. This quantity, rate of change of angular velocity, that is nothing but the rate of change of velocity is acceleration. Here the rate of change of angular velocity is the angular acceleration. That we can denote it as alpha, angular acceleration. Therefore, this tau I can write it as a I alpha. Okay, because alpha is equal to d omega by dt. Here we have simply differentiated the z component of the angular momentum. Therefore, the torque is tau z, and the alpha is equal to d omega by dt is called the angular acceleration. Actually, throughout our discussion, we consider the rotation about only the z-axis. Therefore, in general, I'll write tau is equal to I alpha. I omitted the z notation. And we know that for pure rotation, tau is equal to I alpha. And this is for a rotational motion. Whereas in the linear motion, we know that the force is the mass into acceleration. Okay. Next, our attempt is to find an expression for the kinetic energy of the body, which is in the pure rotation. Actually, we are talking about the motion, the pure rotation of the rigid body, and we derived the expression for the angular acceleration and the torque. Next, our attempt is kinetic energy of a rotating body. That is kinetic energy, we have already derived half mv square. That is, if a rigid body consists of n number of particles, let me write j is equal to 1 to n, and its mass of that single particle is j, mj, and its linear speed is vj, and half mv square. If you do the summation of all masses, then you will get the kinetic energy of this rotating body. Fine. And one more thing we have noticed, if this is the jth particle, and this will be the perpendicular distance to the jth particle from the angle of rotation, that is rho j. Therefore, this v one can rewrite or can be expressed in terms of this rho j, rho omega. Therefore, the kinetic energy half mj rho j square omega square. Fine. Here half we can take an outside, summation over j, mj rho j square omega square. And we have noticed that this term, that is nothing but the moment of inertia, I m r square, moment of inertia. Therefore, the kinetic energy of a rotating body can be written as half I. This whole term is I. The remaining term is omega square. This is the kinetic energy of a rotation. This is similar to the kinetic energy of linear motion of an object, half mv square. The m is replaced by I, and v is replaced by omega. Fine. Now we will do some problems involved in the rotation under applied torque. Look at this problem. It is called Atwood machine with the massive pulley. The picture is given here. The problem is to find the acceleration A for the arrangement shown in the sketch. The effect of the pulley is to be included. That means this is a pulley is having a mass mp, r is the radius of the pulley, and there are two masses m1 and m2 connected with the rope. Now it is shown that the acceleration is downward, this one, and the acceleration of the mass m2 is upward, and it also given that there is an angular acceleration alpha. That is a system, that is mass m1 goes down. Okay, our aim is to calculate the acceleration of the A of mass m1 and mass m2. We need to calculate what is A, and for this it is clearly mentioned that the effect of pulley is to be included. Fine. Now let us start do the problem. See here, if m1 is going down and m2 is going up, then the mass of m1 is larger than mass m2. Therefore, to solve this problem, first assume that m1 is greater than m2. Then the pulley undergoes a pure rotation about its axle. Fine, and the rotation of the pulley is anti-clockwise. Pulley is rotating around this direction. We did this kind of problems, that is to find out the acceleration of the masses. For that, we first to write the equation of motion of mass m1 and mass m2. That is first to draw the free body diagram, or we can write equation of motion of m1 and m2. For this, draw the free body diagram. This is mass m1. We know that its weight will be there in the downward always, and tension is always away from the mass. Therefore, this is a T1. Acceleration of the body is down, down. That is W1 downward. Tension is always away from the mass, and acceleration is downward. And we have the next body, that is mass m2. Its weight is downward always, and tension is away from the mass. Let me write that tension is T2, and its acceleration is upward, W2. Tension away from the mass, it is accelerating upward. Now you can write the equation of motion, that is the W in the W1 weight is acting along the direction of the acceleration, therefore put a positive sign, and the tension is opposite to the acceleration, put minus T1, is equal to m1 into a. For mass 2, the weight is opposed to the acceleration, but the T2 has the same direction as that of acceleration. Put a T2 as a positive sign. Then W2 minus m2a. Equation 1, equation 2. Now it is specified that we need to consider the motion of the rotational motion of the pulley also. Therefore, we need to describe how this pulley gets a rotation. For this, once again, I copy that picture here. Actually, the m1 is larger, therefore the tension T1 is larger and the tension T2 is smaller. Then the imbalanced force, that is we call the T1 minus T2, this is imbalanced force, exerts a torque to this pulley. That is, because of this tension T1 and this one T2, imbalanced force T1 minus T2 exerts torque to the pulley. As a result, the pulley undergoes an acceleration, that is an angular acceleration. We call it as alpha. Okay, the pulley starts rotate along this direction, anti-clockwise direction. That is denoted by angular acceleration alpha. Let me note down this point here. Fine. That is the imbalanced force T1 minus T2 exerts torque to the pulley. As a result, the pulley undergoes angular acceleration alpha. That is the equation of motion of the pulley. Actually, the pulley is undergoing a pure rotational motion, Therefore, this equation of motion is tau is equal to I into alpha. Similar to F is equal to ma, here we tau is equal to I into alpha. Because here the rotation is purely, here the motion is purely the rotational motion. Find the rotational force acting on the pulley. That is, one can write this tau is nothing but R cross F I into alpha. This is R cross F is the general expression for the torque acting on the system. And here if you see this picture, if I redraw that picture here, this is R, and the torque on this pulley is due to the imbalanced force. T1 is larger and T2 is smaller. Okay, T1 is greater than that of the T2. Therefore, it starts to rotate along this direction, and therefore the rotating force, that is the F here, this is nothing but T1 minus T2, and R is this one, and the angle between these two is 90 degree. Here also, if you take R, the angle between these two is 90 degree. Therefore, this is T1 minus T2 into R is equal to I into alpha. Therefore, here I will write that this is a T1 minus T2 into R is equal to I into alpha. You may have doubt that why we have taken T1 in this direction upward, T2, sorry, downward, T2 also in the downward. Then if MP is the mass of the pulley, if you write the tension from these masses, from this MP mass, the tension is always away from the mass. T1 downward, T2 downward. It is already mentioned at the beginning that the T1 is larger than that of T2. Therefore, these two tensions are not equal. This creates an imbalanced force, that is this T1 minus T2. That creates a rotation along the anti-clockwise direction that provides some angular acceleration to the pulley. Now let me write this is equation number 3. Our aim is to calculate this acceleration A. For this, we can add the equation 1 and equation 2. Okay, let me write add equation 1 and 2. That is, equation 1 is nothing but W1 minus T1. If you add this equation 1 and equation 2, here W1 minus W2 plus T2 minus T1, and right hand side we have M1 plus M2, and take A outside. A is common in these two equations. Therefore, let me write W1 minus W2 plus T2 minus T1, right hand side M1 plus M2, we can take A outside. Now we have the T1 minus T2 here and T2 minus T1 here. I write this equation as a T1 minus T2. That is W1 minus W2 minus T1, put a bracket, minus T2. Therefore, minus into minus, you will get plus T2, like this one. Then no issue writing the above equation in this fashion. That is equal to M1 plus M2 into A. Let me put this equation number 4. Now if you look at this equation 3, this equation here, instead of T1 minus T2, I can write I alpha by R. Therefore, I'll mention here 3 in equation 4. Then the equation 3 I can write T1 minus T2 is equal to I alpha divided by R. This is nothing but equation 3. Put that equation here. Therefore, W1 minus W2 is minus. Instead of T1, T2, substitute I alpha divided by R. That is equal to M1 plus M2 into A. Fine. Here the alpha is here. I am looking for writing this alpha in terms of the angular acceleration. For that, the alpha in the question, that is here, this alpha in this picture, this alpha is the angular acceleration of the pulley, angular acceleration of the pulley. And here we assume this rope does not slip. Velocity of the rope is equal to the velocity of a point on the surface of the wheel. Because of this mass difference, the rope is pulled down. When the rope is pulled down, if you consider a point on this wheel, then that point will also rotate with the same as the velocity of the rope. That is, we can say that the velocity of the rope is equal to the velocity of the point on the surface of the wheel. Okay, which means we here assume that the rope does not slip. Okay, let me write these points down. Assume rope does not slip. Therefore, velocity of the rope equal to velocity of a point on the surface of the wheel. Fine. That is, if omega is the angular acceleration and v is the velocity of the point on the surface of the wheel and r is the radius, then the relation is omega is equal to v by r. V is equal to omega into r. Then the acceleration of that point on the wheel, that is simply differentiate this velocity with respect to time. The radius is constant, therefore the differentiation comes with the omega. d omega by dt, the rate of change of angular speed of the pulley, that is nothing but the angular acceleration. Therefore, acceleration A, the linear acceleration, I can connect you to the angular acceleration in this way. Or we can write alpha is equal to A by R. I think let us put this is equation number 5. Okay, now what I will do is, I mentioned I am looking for a substitution for this alpha. I replace this alpha by this expression A by R. That is, we can put equation 5 in equation 4. Okay, maybe you can write this is a equation 6 and the down one is equation 5. Put equation 5 in equation 6. This replace alpha, W1 minus W2, I. Alpha is nothing but A by R. Here one more R is there in the denominator, for this is R square. M1 plus M2 A. Why we did this job? Why we replaced this alpha? Because one cannot easily calculate this alpha. If you are deriving a general expression to calculate the acceleration of the individual masses m1 and m2 in this picture, in the question, then one can easily mention, one can give as in the input parameters m1 what is kilogram, m2 what is a kilogram, and one can give what is the radius of the pulley, mass of the pulley, and with this information you need to calculate the acceleration. If you keep your alpha in the expression, that will be quite difficult to calculate alpha first, then to calculate A. If m1, m2, mp and r are given, then one can easily calculate the acceleration A without finding out the value of the alpha. Therefore, we have to remove the alpha in the general expression of the calculation of the acceleration A. Therefore, we did this some steps to remove the alpha. Now we have alpha common, acceleration common here and here. Bring that A, that is our aim to calculate this A, that is the acceleration of the masses m1 and m2. That is, we have to rearrange the term w1 minus w2 is equal to, I bring this term to right side and take A outside. This is m1 plus m2 plus I divided by r square. Here the acceleration that to be calculated present in the RHS. Therefore, take that A one side, w1 minus w2 divided by m1 plus m2 plus I divided by r square. One can say this is the general expression. However, we can replace this I by the moment of inertia of the disk, because in the question the pulley is of disk type. Therefore, we can replace that I by mr square by 2. That is, if the pulley is a disk, put or take I is equal to mr square by 2 and substitute in the above expression, you will get w1 minus w2 divided by m1 plus m2 plus, instead of I substitute mr square by 2, denominator 1 more r square, got to cancel, and let us mention that the pulley's mass by mp. Therefore, here also we can do mp. Okay, finally the expression for the acceleration of the masses, that is the w1 you can replace m1g, w2 you can replace m2g, and take g outside, you will get m1 m2 g divided by denominator m1 plus m2 plus mp divided by 2. This is the final expression for the acceleration of the masses m1 and m2. Thus, we solved this problem. We have calculated acceleration A. Okay, thank you very much.